There are some people that studied the increase of extreme precipitation, sub-hourly precipitation over the globe. We don't have much data. The feeling is that from the pre-industrial era, the max increases that we can find in extreme precipitation is plus 15%. It's hard to find increases that are above plus 6%. In some part of the globe, extreme precipitation decreased. What is the message that I would like to convey? Sometimes we listen from the television that extreme precipitation intensity has intensified of plus 100%. I heard once a famous climatologist saying that extreme precipitation increased 10 times. This is absolutely unreasonable. When the max increase that was detected by analyzing data is plus 15, plus 18 in Australia. Usually it's around plus 5%, plus 3%. It is something that is really significant. I mean, we don't have to ignore it, but it is significant, but still it's not so dangerous from the point of view of an engineer, because we have safety factor usually, and the usual safety factor that we adopt is plus 50%. The usual number is 1.5 as safety factor, which means plus 50%. A plus 5% is not something that is concerning to us as engineers. It may be concerning from a general point of view, like what's going on. This is maybe a matter of concern, but from a technical point of view, it's important to say that if I get flooded today, it's not for climate change. I'm making it very simple. Of course, you have to be careful in saying this, because any situation is particular. So, for instance, snow floods, floods originated by snowmelt, they may be increased, because 1 degree temperature in terms of snowmelt is very significant. And therefore, you have to be careful when you say, if I get, like I said, if I get flooded, it's not for climate change. Any situation deserves a technical investigation, but on the other hand, we have to bring the problem in its context. Now, sea level rise. So, one question that I could ask you, what is your feeling? Like, what is the sea level rise that we experienced so far? Because everybody is talking about it. And I tell you that when I studied the problem, I decided to make a review about sea level rise. I was a bit surprised by what is the recognized sea level rise from 1850 to today. First of all, it's not constant, because it depends on aerostatism, change of altitude of the land, and it depends also on the fact that sea level is not constant. There are changes. But anyway, if we make a global average, we are talking about 15 centimeters of sea level rise from 1850 to today. And this is a progress of sea level rise starting from like 20,000 years ago. So you see that there was a change from the last glacial maximum of about, this is in meters. So there are indeed changes that are tens of meters due to glaciations. Now, if we look at a global, the same picture more or less, with the rise originated by the warming that we are experiencing today, you see that it's just a very small component with respect to the changes in sea level that were originated by glaciations. And this is a map. This is a map of the Earth. In red, what can you see here? This is a map of the areas that would be flooded if we experienced a sea level rise of 6 meters. 6 meters is, why 6 meters? Because when we talk about predictions of future sea level rise, up to 2100, and if you start from considering that in the past 150 years we had a sea level rise of 15 centimeters, from a technical point of view, we may say that the sea level rise may be plus, with respect to today, up to 2100, like plus 30 centimeters. This is already a skeptical evaluation. And therefore, it's not comparable with the 6 meters. But there are theories that postulate that there might be a threshold beyond which the ice cap suddenly melts. So there are theories that assume that the melting of the ice cap is not something that progresses slowly, but there might be a threshold beyond which we get a sudden melt. And there are estimates of sea level rise due to complete melting of the ice cap that predict that the sea level would increase 6 meters. So these are the extreme predictions. So we can range from plus 15, 20 centimeters from now to plus 6 meters if there is a complete melting of the ice cap. If this happens in red here, you see the areas that will be flooded with the plus 6 meters. Still, it would be nothing with respect to what happened in the past due to glaciations, but anyway, of course, if it is 6 meters, it's something that may be concerning. Let me go back. I don't know why, but okay. Now let's look at the recent past. This is the sea level change from 1880 to today, and you see that we are in the range of plus 15. And there are several reconstructions. This is an average of several reconstructions. And keep in mind that the sea level is measured from 1950, so in order to go back to 1880 we need reconstructions. And it's not constant over the globe. There are several graphs that can be shown. This is a recent sea level rise from 1990. And from 1919, these are millimeters, and therefore we are talking about 1.5 centimeters from 1990. Look, if I go back to the past graph, you see that there was from 1980 to 1990, there was a decrease in sea level, which is not clearly explained. And then, if we look at from 1990, there is this increase, about 1.5 centimeters. Okay, and this is, that's it. And this is a map of sea level rise from 1992 to 2013. This is in millimeters per year. The very max is 9 millimeters per year. And the blue is -7. 0 is white. And the global average is about orange, which means 1 millimeter per year, which is reflected in the previous graph. And you see that indeed the sea level rise is not constant for several reasons. Okay, this is the picture that emerged from the numbers, from the data. And these are some predictions. I leave this table to you, and this is prediction in meters. So if we look at the last column up to 2100, and you see that this is depending on the increase in temperature. So this is mean increase in temperature, 1 degree, 3.7. And if we accept an increase of 3, let's look at the extreme. Let's look, for instance, at 3.7 degree of increase. The prediction of the sea level rise, according to climate models, is from 0.45 to 0.8. Of course, this does not include the assumption of sudden melt of the ice cap. So the prediction of the IPCC is an institution, is a body that tries to evaluate the effect of climate change, and it tries to be very objective. The prediction for, again, an increase in temperature that is very high, because it's 3.7, it's in the range 40 centimeters, 80 centimeters. Okay, and that's it. If we look at the water cycle, which is not our direct interest, and if we look at floods, there is no, I summarize, there is no evidence that floods are increasing after climate change. There is evidence that in some countries floods are indeed increasing, and especially the damage caused by floods is increasing. And the reason is, in most of the cases, land use change and increased exposition. Exposition means value of the flooded areas. So the damage is increasing because the value of the areas is increased. Okay, and let's forget about these graphs. And this is a picture of flood changes in Europe as detected by a recent studies. So you see that there are some regions where floods are increasing and some regions where floods are decreasing. It depends on the origin of floods. As I said, where floods are mainly caused by snowmelt, we have an increase. Where they are caused by other factors, like extreme rainfall, they are not increasing much. Okay. Keep in mind that this data usually refer to specific situations, like big rivers are easy to measure. Small creeks are responsible sometimes of tremendous floods, but are not easy to measure. And therefore, most of these data refer to particular situations. And therefore, the criticism with respect to these studies is that they cannot measure everything. And some people assume that what we cannot measure has worsened a lot. Maybe indeed. Okay, and let's forget about this. And these are some predictions by climate models, and you see that with respect to the pre-industrial situation, which is like with respect to the global average minus 0.5, up to 2100, some of them predict, this is without CO2 limitation, without the limitation of CO2 emissions. Some of them predict a plus 2.5, and some of them even predict a plus 5. Now, what can we do with climate change? We can act in two ways, with mitigation and adaptation. Keep in mind the difference between these two words. There is a fundamental difference. Mitigation means that we mitigate climate change, we reduce it. Adaptation means that we take climate change for granted and we try to adapt. Our main issue as engineers is adaptation. Let's leave mitigation to other scientists, to other people. We are engineers, and adaptation is our business. And therefore, we have two questions. First, how to quantify future climate, how to generate future climate scenarios. Second is what to do. Once we estimated the design variables, how can we adapt? And here there is a climate change adaptation. And how to generate future, these are some solutions that can be adopted in general for adapting to climate change. They do not specifically refer to coastal areas. So how to generate future climate scenarios. Some people use climate models. Keep in mind that climate models are not conceived for the purpose of engineering. They are conceived for providing scenarios, which means possible pictures of future climate. And the term scenarios perfectly gives the essence. Now, the scenario cannot be used for engineering because we need, instead of scenarios, we need a figure, which is an estimate of a design variable. If there is uncertainty, we need also an estimate of uncertainty. So, we cannot take the prediction of climate models as they are for engineering. So this is a bit of a problem because prediction of climate models are easily available. To generate technical predictions, it's a challenge because the question is how can we predict in technical terms the future climate? There are possible several solutions that can be adopted. The first is empirical, and everything is described here. The first is empirical, like basing on your expert knowledge, perception, you estimate a possible future change. And I don't know for what reason, many people say plus 20%. And therefore, for precipitation, for water shortage, sometimes I speak with technicians, and they say, let's assume that I have minus 20% of water in 50 years. Actually, the reason why they say minus 20% is that it's a reasonable number. It doesn't have an unsustainable impact on the design, because if you say minus 80%, it may become unsustainable from the point of view of the design. Because if you say, like, I want to protect a coastal area for an increase in the extreme wave height of 80%, it may be unsustainable. You cannot protect against it. And therefore, of course, there is no solution. If you say increase of 10, 20, 30%, in most of the cases is sustainable, meaning that it's possible and it's economically viable. On the other hand, it's already a plus something. I mean, usually when we estimate uncertainty, we don't plus 20% is something that means already precautionary choice. So this is one possibility, like let's empirically estimate a future change. And this is something that you can agree with your stakeholders. A second possibility is that you estimate, you assess the variability of your design variable based on data. Like, I take measurement of wave height and I estimate variability based on data. This variability doesn't include climate change, or it includes climate change only for the past 15 years. So, by itself, it's not enough. This variability is quantified through statistical models. And this is something that we know how to do. Maybe that specifically you don't know how to do it, but it's part of the usual background of engineering, and if you still don't know how to do it, it's easy to learn. So you estimate variability. And then you get a climate model telling you how much variability can change. So climate models are used for predicting the change in statistics, not for predicting the change in numbers. And this is a safer approach, because statistics are estimated by models with reduced uncertainty with respect to individual numbers. And therefore, as I said, you create a statistical model to reproduce the known variability, and then you change the parameters of the statistical models, which are the statistics, according to prediction by climate models. This is a possible solution. This is what is called stochastic simulation. It's briefly described somewhere here. And yes, it's briefly described here. So keep in mind just the essence of the concept, which is climate models cannot be used by themselves for technical design. And if you get proposed to do that, be cautious. My suggestion is just be careful, be very careful, because your design may become unsustainable. Okay, basically that's it. Do you have any question on this? Okay. Let me just check the email, because I am concerned by that guy that if he doesn't come, I'll get a bit upset. Just give me 1 minute. No reply. Okay, now, questions. Okay. Can I ask you a question? I gave you some orders of magnitude. Plus 6-10%, 20% extreme rainfall, plus 15 centimeters of sea level rise. And can you please raise your hand if you were expecting this, or let me formulate it in a better way. Raise your hand if you expected more changes, if you expected that climate change affected already more than what I described so far. Raise your hand if you were expecting more. Nobody, I can't believe that. Okay. And raise your hand if you were expecting kind of this order of magnitude. Okay, and there are people who didn't have any idea. Raise your hand if you believe that climate change is a fake news. Okay.
It's mild and it's still winter.
Sorry?
It's mild and it's still cold.
You know, I think it's not a fake news, but I think it is an exaggerated claim. And this is my personal perception. I think we have some threats to sustainable development that are much more concerning with respect to climate change. Climate change, anyway, is not a fake news. I think it is a threat. But there are other threats that are more concerning, like saltwater intrusion. Saltwater intrusion, I think it's more threatening for coastal areas with respect to climate change. And another, if I refer to freshwater resources, I think water quality is a more concerning threat, because, you know, water quality indeed is something that we have to take care about. But
Prof, we are talking just about from a engineering point of view, or something related to the environment in general?
no, I would say, let me better. I would say that if I make reference to the environment that I know, like Italy, for instance, because of course, if you refer to a flat island, is a different story. But if I refer to Italy, I think that the coasts of Italy, the environment of Italy, and the floods in Italy, water resources in Italy, are threatened more by water quality, saltwater intrusion, and rather than increasing extreme precipitation. Land use change is another threat, or uncontrolled urbanization. So in Italy, we have an increasing damage due to floods. And I am very concerned by the fact that people claim that it's for climate change, while indeed it's given by the fact that we build houses very close to rivers. And why I am concerned? Because in order to solve a problem, you have to identify the driver, the causes of the problem. And if we keep saying that floods in Italy, the increase of floods in Italy, the increase of deaths by floods in Italy is given by climate change, we don't solve the problem because people keep building houses where they should be removed instead of building them. But the problem is that when your problem has a local explanation, it doesn't become interesting for the media. And the climate change is interesting for the media because it's a global problem. And if you talk about uncontrolled urbanization, who cares? Like, if you look at the increase of death in Africa for floods, there is a clear increase of death. And we are talking about thousands of people who die. Also in Italy, we are talking every year. Tens of people that, on average, not tens, but every year we have death in Italy for floods. And if you look at Africa, it's clear that the reason is uncontrolled urbanization close to rivers. And I can't really accept that we don't find this explanation interesting, because it's a local problem, so people just say, who cares? And they wanted to build the houses close to river. It's not a problem for me, because it's just enough that I take care of not getting close to the river. So it's not a problem relevant to everybody. Climate change is something that is relevant for everybody, and therefore it becomes important and controversial. Controversial because we blame the Chinese, we blame the Americans, because Trump administration doesn't fight against climate change, and this is why the media are so interested, because it's controversial and global. Okay, let me go back to the page of the course, and there is a last lecture that I included here, because I was planning to say something today, which is design of breakwaters. Design of breakwaters, that my treatment is very limited, because I know that Professor Archetti already talked about breakwaters, and this lecture provides, at least as far as I know, because I spoke with Professor Archetti, but not recently, provides additional information on breakwater design. And now I'm opening it, but it's not my intention to give this lecture, because I want to use the remaining time that we have to wrap up. I just wanted to give to you an explanation, because I suggest you to read it, but at the exam I will never ask anything about breakwater design. Okay? I may ask something about breakwater, but not design. And here I am concentrating, but as I said, I suggest you to read it, because I think there are some additional information with respect to what Professor Archetti told you, because she focused particularly on harbor protection, if the information is correct. Now, here there is a general treatment and a scheme of how a breakwater is built, and I think this is probably the same, was already covered by Professor Archetti. And what is, I don't think she talked about wave run-up and overtopping, how to estimate wave run-up. And I am proposing some empirical formulations here. And what I am talking about in particular is wave transmission, which means that when you have waves approaching a breakwater, you have also an effect on the lee side. The lee side of the breakwater is the part that is included between the breakwater and the land. So part of the waves are transmitted. This happens if the breakwater is overtopped. Okay? And here there are some rule of thumb for estimating wave transmission above a breakwater. I think this is important, and I'm not sure Professor Rocchetti discussed about it with you. There is another issue I am discussing, which is the water setup induced by breakwaters. What is the water setup? When you have a breakwater, so you have your breakwater, sorry, there is the seabed, and over the seabed you have breakwater. Okay, very simple. Let's suppose that cannot be overtopped. If you have waves approaching the breakwater, and let's suppose that they don't pass over the top of it, what you get, let's suppose that this is the mean sea level. What happens is that if the breakwater is permeable, and several of them are permeable, you get either through the breakwater or through the breaks, the apertures, you get some water getting into the lee side. As I said, either through permeability or through the apertures. And then this water has to flow back. And the way the water can flow back is by establishing a higher water level in the lee side. So in the lee side, you get a water level, an average water level, that is higher with respect to the average water level on the offshore side. And this is the setup. And sometimes this is important, especially for coastal protection. The setup is important. Of course, the setup is occurring only when you have waves approaching breakwaters, and depending on the wave height, the setup increases. And here you can see some empirical formulas for estimating the setup. So you need a higher energy in the lee side in order for water to flow back. And that's it. Okay. Now, what I would like to do with you now is, as I said, to wrap up, which means let's go back, open lecture by lecture, and highlight what are the questions that I may ask at the exam. Just to give some examples, I see your interest, I know that this is interesting. Okay, so let's forget about the first lecture, because if you remember, we talked here about the learning process, etc. No questions at the exam, okay? Coast management and beach design. Here is a general premise. Usually I don't ask any question, but it may be if I want to give if I want to ask you a very quick question, I may ask you something like, what is a landlocked country? Or how do you call a country that does not have any access to sea? So remember that I may ask some basic definitions sometimes, like how do you measure wave height? And sometimes the students get in trouble because they don't remember whether the height is the same as the amplitude or not. Okay? So keep in mind definitions. I may ask them, like, what is wave amplitude? It's the same thing as wave height. And what is wave period? And in this case, if I look at this picture, sometimes when I am during the exam, I take my PC and I look at the lectures in order to get inspiration for the questions. So if I see this picture, I may ask you, okay, what is a landlocked country? And another possibility could be, how would you define a coastline? And then, I don't see anything interesting here. Okay, I wouldn't say that it's, or I may ask you why, it's difficult, but just why beaches are important. What type of coasts we discussed? Beaches, cliffs, cliff coast, etc. Now, mechanics of sea waves, usually I don't ask anything, but sometimes I may ask, can you please derive the Laplace equation? this one. You studied it with Professor Archetti, okay? With the 0 on the right-hand side, it's easy, okay? Easy, I mean, it's something that you studied. I may ask myself this, okay? Laplace equation, sometimes I ask it. But that's it. I'm not asking anything more about wave mechanics. Wave transformation, of course, I may ask you what is wave refraction, what is wave diffraction, what is Scholling, what is bottom friction, and wave transformation I can ask you definitions, okay? But you studied also with Professor Archetti this, so I don't think it is concerning for you. I may ask you what are the strategies for these protections, and this is just very descriptive, but it's an ideal first question, because I assess your ability to speak. I let you speak about 10 minutes. So what are strategies? Breakwater, groins, beach nourishment, bypass, seawalls, or breakwater with breaks. And try to, if I ask first a descriptive question, and try to be synthetic, but at the same time comprehensive. And this is ability. Ability means to be able to speak for the right amount of time by providing a comprehensive overview. And another thing, because I want to be clear, I mentioned to you when I make the exam, I make the exam to 2 students at a time, which means that for a reduced number of students, I start with the first question that is oral, meaning that I allow you to speak 10 minutes, etc. With most of the students, the first question is written, which means that I ask you to write your response over a sheet, and then when it's your turn, I ask you to present me what you wrote. And so the descriptive question, maybe not the